Welcome to the Science Salah Lotfy Channel. Today, I'm diving into a key challenge shaping the future of nuclear energy in Brazil, the process of commercial-grade dedication, or CGD. In a world striving for clean, reliable energy, nuclear power stands out as a powerful solution. But building and maintaining a safe nuclear infrastructure isn't easy. Brazil, with its growing nuclear ambitions, is facing a critical hurdle: how to safely integrate non-nuclear commercial-grade components into its nuclear systems. So, what exactly is commercial-grade dedication, or CGD? It's a rigorous process that ensures industrial components, not originally designed for nuclear use, meet strict nuclear safety standards. This means testing, verifying, and qualifying these parts to perform reliably in a nuclear environment. Brazil currently faces several technical challenges: a lack of in-country labs and infrastructure capable of performing CGD testing, limited access to detailed regulatory guidance based on global standards, and difficulties in sourcing certified suppliers who can provide adequate documentation for CGD approval. This bottleneck slows down the expansion and maintenance of nuclear facilities. Yet this challenge presents a valuable opportunity. Adopting a robust CGD framework can lower costs significantly. Commercial parts are often cheaper than custom-built nuclear-grade items, as long as they are properly tested. It also opens the door for local industries to step in and become part of the nuclear supply chain, stimulating innovation and industrial growth. The impact goes beyond industry. Expanding Brazil's nuclear capacity enhances energy security and helps meet the country's growing electricity demand. And by investing in CGD infrastructure, thousands of new engineering and technical jobs could be created across the nation. Scientifically, Brazil has the chance to become a leader in Latin America. By building a reliable, localized CGD system, Brazil can share its expertise with other nations facing similar challenges. This promotes international cooperation and advances global nuclear safety standards, especially in developing countries. Brazil's journey with CGD reflects a broader truth. Nuclear energy is not just about reactors, it's about systems, standards, and trust. By overcoming its CGD challenges, Brazil can power a safer, smarter, and more independent future. Thanks for watching. This is the Science Salah Lotfy Channel, where we bring research to life. Welcome to the Science Salah Lotfy Channel. In this video, we highlight a vital topic from the Brazilian Journal of Radiation Sciences: commercial-grade dedication challenges for the Brazilian nuclear industry. This research, published in Volume 83A, 2020, was authored by Dr. Rosa Baliza from Eletronuclear, Dr. Youssef Morghi, and Professor Dr. Amir Zacarias Mesquita, both from the Nuclear Technology Development Center, CDTN in Brazil. Brazil's nuclear industry plays a crucial role in the country's energy strategy. At the heart of this research lies a technical and regulatory challenge. How can Brazil safely use commercial-grade components in its nuclear power systems? This process is called commercial-grade dedication, or CGD. CGD involves testing and verifying that ordinary non-nuclear parts meet the safety and performance standards required in nuclear reactors. It's a critical process, one that ensures reliability, safety, and cost-effectiveness in nuclear power generation. The study emphasizes several challenges in Brazil: limited access to dedicated testing laboratories, gaps in regulatory guidelines aligned with international standards, and the need for specialized technical training to carry out CGD effectively. Thanks to the work of Dr. Rosa Baliza at Eletronuclear, Dr. Youssef Morghi, and Professor Dr. Amir Zacarias Mesquita at CDTN, this research outlines a clear path towards strengthening Brazil's nuclear safety infrastructure. Building a safe and independent nuclear future requires more than just technology; it takes rigorous standards and local expertise. Brazil is rising to that challenge. Stay curious, stay informed. This is the Science Salah Lotfy Channel, bringing research to life. Commercial-grade dedication, or CGD, is a process of transforming everyday items into crucial components for nuclear power plants. Imagine taking a regular wrench, the kind you might find in your garage, and making it strong enough to handle the immense pressure and radiation inside a nuclear reactor. That is the essence of CGD. It's about rigorously testing and documenting these ordinary items to ensure they meet the stringent safety standards of the nuclear industry. This process allows us to utilize readily available materials and turn them into vital parts for our power plants. CGD is not about cutting corners. It is about smart engineering and resourcefulness. In a world facing climate change, it is about finding innovative ways to make nuclear power, a carbon-free energy source, more accessible and sustainable. By adapting existing technologies and materials, we can reduce our reliance on expensive and often difficult-to-source nuclear-grade components. This approach makes nuclear energy a more viable option for countries like Brazil, looking to diversify their energy mix and reduce their carbon footprint. Brazil has a long and complex relationship with nuclear energy. The country currently operates 2 nuclear power plants, Angra 1 and Angra 2, which provide a small but significant portion of its electricity. However, both of these reactors are approaching the end of their designed operational life. Angra 1 in particular is over 40 years old and relies heavily on imported parts, making maintenance increasingly challenging and expensive. This reliance on international suppliers for specialized components exposes Brazil to potential supply chain disruptions, geopolitical tensions, and fluctuating costs. Furthermore, as reactors age, finding replacement parts becomes increasingly difficult. Manufacturers often discontinue older models, leaving plant operators scrambling for solutions. This is where CGD offers a beacon of hope. Imagine a doctor revitalizing a patient's health by replacing worn-out organs. CGD functions similarly for nuclear power plants. This process allows us to breathe new life into aging reactors like Angra 1 and 2. By sourcing readily available commercial-grade components and dedicating them to nuclear-grade standards, we can significantly extend the lifespan of these plants. This translates to continued clean energy production, reduced reliance on fossil fuels, and a more sustainable energy future for Brazil. The beauty of CGD lies in its adaptability. It's not a one-size-fits-all solution, but rather a tailored approach. Each component, whether it's a valve, pump, or even cabling, undergoes a rigorous evaluation process. This includes material analysis, performance testing under simulated reactor conditions, and meticulous documentation. Only after passing these stringent tests can a component be deemed suitable for use in a nuclear environment. Section 4, CNEN, Brazil's Nuclear Guardian. In Brazil, the safety and reliability of nuclear power fall under the watchful eye of the Comissão Nacional de Energia Nuclear, or CNEN. This regulatory body plays a crucial role in overseeing the implementation of CGD within the country's nuclear facilities. CNEN sets the standards, reviews the testing protocols, and ultimately approves the use of commercial-grade components in safety-critical applications. Their involvement is not merely bureaucratic, it is a critical layer of safety, ensuring that the highest standards are maintained throughout the CGD process. This meticulous oversight fosters trust and confidence in the use of CGD, both within the industry and among the public. CNEN's role is essential in demonstrating that safety remains paramount even as Brazil explores innovative approaches to maintaining its nuclear fleet. Section 5, A Safer Future, CGD for Energy Security and Industrial Growth. As we look towards a future increasingly powered by clean energy, CGD emerges as a key enabler for countries like Brazil. By embracing this technology, Brazil can reduce its reliance on foreign suppliers, creating a more resilient and self-sufficient energy sector. This translates to greater energy security and shields the country from potential global supply chain disruptions. But the benefits of CGD extend far beyond energy security. Implementing CGD fosters technological innovation and stimulates local industries. It creates a demand for specialized testing facilities, engineering expertise, and high-quality manufacturing. This translates to job creation, economic growth, and the development of a highly skilled workforce. By investing in CGD, Brazil invests in a brighter future, one powered by clean energy and driven by technological progress. Welcome to the Science Salah Lotfy Channel. Today, I'm diving into a process that's crucial for the safety and reliability of nuclear facilities, the dedication process for commercial-grade items. Not every component in a nuclear power plant starts off as a specialized nuclear-grade item. Many are actually commercial-grade parts like screws, bearings, or lubricants that undergo a transformation process called dedication. This ensures they can perform safely in a nuclear environment. Take a look at this list. Items like resistors, relays, connectors, fuses, and integrated circuits, though produced for commercial use, can be evaluated and approved for nuclear systems once proven to meet equivalent quality and safety standards. So how does the dedication process work? It involves two major steps: technical evaluation and acceptance methods. Together, they form a comprehensive framework that ensures the commercial item meets all nuclear requirements. Step 1 is the technical evaluation. This involves verifying whether the commercial item can meet the specifications of a qualified nuclear component. It includes checking documentation, assessing reliability, and identifying critical characteristics. If the item is identical to a previously qualified one, the process is simpler. But if it's just similar, not identical, a full technical assessment must be done to avoid wasting time or approving the wrong item. Evaluators examine the manufacturer's quality program, product performance history, and available technical data to justify the start of the dedication process. All findings must prove that the item can operate reliably under nuclear conditions. Next come the acceptance methods. These are the tools to validate that the item truly meets all requirements. Techniques like functional testing, source verification, and inspection must offer reasonable assurance that the commercial item will perform the same safety function as a nuclear qualified component. In Brazil, the standard followed is CNEN 1.16, which aligns closely with the American 10 CFR 50 Appendix B. So whether the dedication is done by a utility, a supplier, or a third-party entity, it must comply with these strict quality assurance requirements. Before proceeding with dedication, engineers must determine the safety function of the item. Does the component have an active role, like a valve or a relay, or is it passive, like a pipe or bracket? Both may play crucial roles in maintaining safety. Nuclear facilities maintain databases that classify equipment and systems based on safety importance. Engineers must consult updated diagrams, material lists, and design documents to identify the item's function within the system and assess its safety role. It's also important to evaluate whether the item must withstand seismic activity or environmental extremes, such as radiation, high temperature, or pressure changes. This analysis helps identify critical characteristics and possible failure modes that could compromise nuclear safety. And here's a vital point: the dedication process is also a defense against low-quality or counterfeit parts. Only components that truly meet nuclear-grade performance criteria should be approved. Anything less could pose serious safety risks. Ultimately, the dedication process protects lives and ensures the long-term safety of nuclear operations. It combines engineering expertise, rigorous testing, and quality controls, so that commercial parts can serve in one of the most demanding environments known to science. If you found this explanation helpful, don't forget to like, subscribe, and share. This is the Science Salah Lotfy Channel, bringing nuclear knowledge closer to everyone. Thank you for watching. Welcome back to the Science Salah Lotfy Channel, where we delve into the fascinating world of nuclear science and engineering. Today, we're tackling a crucial aspect of nuclear safety and industrial quality control: the dedication of commercial-grade items for use in critical applications. In the nuclear industry, we can't just use any off-the-shelf component. We need to be absolutely certain that every single item, from the smallest sensor to the largest pressure vessel, meets stringent safety standards. That's where dedication comes in. This video will guide you through the 4 primary methods used to ensure that components originally intended for non-nuclear use can be deemed acceptable for these critical applications. We'll break down each method, explore its strengths and limitations, and discuss when it's most appropriate to employ each one. So, whether you're a seasoned nuclear professional or just starting your journey in this field, stick around and let's enhance our understanding of nuclear safety together. Let's get started. The first method we'll explore is all about putting the component itself through its paces, conducting special tests, inspections, or analyses. This approach focuses on verifying that the item in question truly possesses the critical characteristics required for its intended use in a nuclear facility. Think of it like this. Imagine you're installing a temperature sensor in a reactor coolant system. You need absolute confidence that this sensor will accurately measure temperature and respond reliably, even under extreme conditions. That's where method 1 comes in. It allows us to directly assess the item's performance against established standards. These tests can be carried out at various stages: before you receive the item, after it arrives at your facility, or even after it's been installed in the system. The timing depends on the specific item and its intended application. For instance, certain tests might require specialized equipment only available at a dedicated testing facility, while others might be more practical to perform once the item is in its final location. Method 1 is particularly well suited for situations where the item you need is available from multiple manufacturers. This is because it allows you to evaluate each manufacturer's product on its own merits, ensuring that you select the one that best meets your specific requirements. It's also a good option when dealing with relatively simple items, where the critical characteristics are easily measurable and verifiable through testing. Another scenario where Method 1 shines is when post-installation checks are the only feasible option. Sometimes, due to the nature of the item or the system it's being installed in, it's simply not practical or even possible to conduct extensive testing beforehand. However, it's important to note that Method 1 does have its limitations. To effectively implement this method, you need access to certain crucial pieces of information. This includes detailed drawings, specifications, and manuals that clearly outline the item's design, materials, and performance characteristics. Without this information, it becomes extremely difficult, if not impossible, to develop meaningful tests and establish appropriate acceptance criteria. Furthermore, you need to have clearly defined standards against which to compare the test results. If, for any reason, you're unable to obtain the necessary documentation or access to critical information, perhaps due to intellectual property concerns, then Method 1 might not be the most suitable approach. Now let's shift our focus from the item itself to the company that manufactures it. Method 2, known as the Commercial Grade Survey or CGS, takes a deep dive into the manufacturer's quality assurance program. Instead of just examining the final product, we're assessing the entire system that produced it. The fundamental principle behind Method 2 is to determine whether the manufacturer's quality control system aligns with the rigorous standards expected of qualified nuclear suppliers. In essence, we're trying to gauge if their everyday practices meet the high bar set by the nuclear industry. This method proves particularly valuable in a few key scenarios. Firstly, when you're dealing with an item that's only produced by a limited number of manufacturers. In such cases, conducting individual item testing, Method 1, might not be feasible or cost-effective. Instead, it makes more sense to evaluate the manufacturer's overall quality system. Secondly, Method 2 comes in handy when detailed information about the item itself is scarce or unavailable. If you don't have access to the drawings, specifications, and other technical documents needed for Method 1, a CGS allows you to gain confidence in the item's quality by scrutinizing the manufacturer's processes. Thirdly, if you have multiple facilities that require the same item, a CGS can be a more efficient approach than conducting separate item-specific evaluations for each location. By assessing the manufacturer once, you can streamline the dedication process for all your facilities. And finally, Method 2 offers a solution when direct testing of the item is simply not practical or possible. This could be due to the item's complexity, its size, or the nature of the tests required. To illustrate this point, let's consider an example from Brazil. Their nuclear regulatory body, CNEN, has established specific quality assurance standards outlined in document CNEN 1.16. When using Method 2 in Brazil, the dedication process needs to demonstrate alignment with these specific requirements. The dedicator, or a designated contractor acting on their behalf, conducts a thorough evaluation of the manufacturer's quality program. This evaluation focuses on confirming that the manufacturer has robust controls in place to ensure that the critical characteristics of the item are consistently met throughout the production process. The entire survey process needs to be meticulously documented in a CGS plan. This plan serves as a roadmap for the evaluation and a repository for all findings. Chapter 3. Method 3. Source verification. This method takes a hands-on approach, emphasizing direct observation and involvement throughout the item's manufacturing process. It's about witnessing firsthand how the item is made, and ensuring that critical quality attributes are controlled at every stage. Unlike Method 2, which focuses on the manufacturer's overall quality system, Method 3 zeroes in on the specific production run of the item in question. The dedicator or their representative is present at the manufacturer's facility, actively monitoring key manufacturing steps. Now, while it's certainly advantageous for the manufacturer to have a nuclear-grade quality program already in place, it's not a mandatory requirement for using Method 3. The dedicator assumes the responsibility of monitoring and verifying that the critical characteristics are met, regardless of the manufacturer's existing quality system. Source verification can encompass a wide range of activities tailored to the specific item and its critical characteristics. This might include non-destructive testing or NDT techniques like ultrasonic testing, radiography, or eddy current testing are used to inspect the item for internal flaws or defects without damaging it. Performance checks. These checks involve testing the item's functionality to ensure it operates according to specifications. For example, a valve might be subjected to pressure tests to verify it can withstand the required operating conditions. Final inspections. A thorough visual and dimensional inspection is carried out to ensure the item meets all drawing and specification requirements. Calibration and material controls. For items where accuracy is paramount, like instruments or measuring devices, calibration procedures are witnessed and documented. Similarly, for items with specific material composition requirements, the dedicator might observe and verify material control measures. Each step of the manufacturing process that's subjected to source verification is carefully documented. This documentation includes details such as observations, what the dedicator witnessed during the observation, including any deviations from established procedures or specifications. Critical characteristics checked, a clear record of which specific quality attributes were verified during the observation. Chapter 4, Method 4, Acceptable Supplier or Item Performance Record. Finally, we arrive at Method 4, which takes a retrospective approach, relying on the historical performance of the supplier or the item itself. This method hinges on the principle that past performance can be a predictor of future results. It involves evaluating the track record of the supplier or the specific item to determine if it warrants acceptance for nuclear applications. The foundation of Method 4 lies in the meticulous collection and review of performance records. This documentation can include a variety of evidence such as certificates of conformance. These certificates, often provided by the manufacturer, attest that the item meets the specified requirements. They typically outline the applicable standards, the test methods used, and the results. Test reports. Detailed reports documenting the results of various tests conducted on the item, either by the manufacturer or an independent testing laboratory. These reports provide objective evidence of the item's performance against specific parameters. Quality system audits. Reports from audits conducted on the manufacturer's quality management system, either by an external certification body or the dedicator's organization. These audits assess the effectiveness of the manufacturer's quality system in meeting specified standards. Field performance data. If available, data on how the item has performed in similar applications or environments can provide valuable insights into its reliability and suitability for nuclear use. This data might come from other nuclear facilities, research institutions, or industrial settings with comparable operating conditions. It's important to note that Method 4 is generally not used as the sole basis for accepting an item for nuclear use, especially for critical applications. The reliance on historical data inherently carries a degree of uncertainty, as past performance is not always a foolproof guarantee of future behavior. However, when supported by other evidence and a thorough evaluation, Method 4 can serve as valuable supporting documentation. It can strengthen the case for accepting an item, especially when combined with other dedication methods. The dedicator plays a crucial role in evaluating the adequacy of the performance records. Conclusion. Choosing the right dedication method. To summarize, Method 1, testing and inspection of the item itself. Method 2, surveying the manufacturer's quality assurance program. Method 3, monitoring the item's manufacturing process. Method 4, evaluating performance records and documentation. Each method has its place, and sometimes they are combined for a robust dedication strategy. For example, you might conduct a CGS Method 2 to evaluate the manufacturer's overall quality system and then supplement it with source verification, Method 3, for certain critical manufacturing steps. Or, you might use Method 1 to perform tests on a sample of items, and then use Method 4 to review the performance history of those items in similar applications. Choosing the right method, or combination of methods, depends on a variety of factors, including item complexity. Simple items with easily verifiable characteristics might lend themselves well to Method 1, while more complex items might require the comprehensive approach of Method 2 or 3. Availability of data. If detailed drawings and specifications are readily available, Method 1 becomes more feasible. However, if such data is scarce, Method 2 or 3 might be more appropriate. Manufacturer cooperation. The willingness of the manufacturer to grant access to their facilities and provide documentation is crucial for Methods 2 and 3. Operational risk. The criticality of the item's application and the potential consequences of failure will influence the level of rigor required in the dedication process. Ultimately, the goal is to select the most efficient and effective method or combination of methods to achieve the required level of confidence in the item's suitability for its intended nuclear application. Thank you for watching. If you found this video insightful, support the Science Salah Lotfy channel by liking, subscribing, and sharing this content. As we come to the end of today's episode, Science Salah Lotfy Channel would like to express sincere appreciation and gratitude to the researchers whose valuable work made this discussion possible. First, we thank Dr. Rosa Baliza from Eletronuclear, specifically based at Eletronuclear Central Nuclear Almirante Álvaro Alberto, located in Itaúna, Angra dos Reis, Rio de Janeiro, Brazil. Dr. Baliza's work at the heart of Brazil's nuclear operations continues to make a significant impact on national energy strategy and nuclear safety. We also extend our thanks to Dr. Youssef Morghi from the Nuclear Technology Development Center, also known as CDTN, in Belo Horizonte, Minas Gerais, Brazil. Dr. Morghi's expertise and contributions have been vital to the technical evaluation and advancement of nuclear component qualification systems, and we proudly acknowledge Professor Dr. Amir Zacarias Mesquita, a distinguished professor at the Nuclear Technology Development Center under the Brazilian Nuclear Energy Commission, known as CDTN CNN, also based in Belo Horizonte. Professor Dr. Mesquita is widely recognized for his academic leadership and scientific research in nuclear technology development, both in Brazil and internationally. To all three researchers, Dr. Rosa Baliza, Dr. Youssef Morghi, and Professor Dr. Amir Zacarias Mesquita, we offer our deep respect and gratitude for your scientific dedication and the insight your work brings to this global field. And to our viewers, we thank you for joining us on this scientific journey. If you found today's episode valuable, let us know what you think. Leave your comments below the video and share your thoughts about the research. We would love to hear your opinions, questions, or even personal reflections on the importance of nuclear safety and engineering innovation. This is the Science Salah Lotfy Channel, bringing research to life. Until next time, stay informed and stay inspired.